Okay, hello. This is the start of the recording and volume check for all of you joining live as well. I'll move that in the corner. Let's put this here. Yeah, okay. There we go. So, two back-to-back sections. Like, I don't know. Normally, if I'm in the third floor Centennial, I'll just stay in the room, right? And erase the things that I drew on the slides or whatever. And was doing that, but then I don't know. It's different being stuck indoors like this. So of course, I went outside just for a moment, right, just to breathe some fresh air, and there was the cutest dog. That's all. That's all I wanted to just share that. I think it was a bloodhound. Anyway, all right. I move that over here. My set. Yeah. Okay. We'll start with announcements. It is Wednesday, May 6th. There is one last online quiz that will be tomorrow, so I thought it's just good to make mention of it today. I will mention it tomorrow, of course. I would say, with WebWork, please start WebWork 44. I believe that's the last one. Um, Start it today. Today's the day I would really prefer you start it. Even if you don't finish it today, it's the final due date is during finals, so it is extra credit. And I should actually comment related to that, just with how the timing of things work. It's like because of when the final exam is open on Tuesday the 12th, I needed to, for this to be any use, had to make this due, Monday. So there's actually two WebWork assignments due on Monday finals week, so I made both of those extra credit. There's didn't know what to do. So, office hours through the remainder of the semester are posted here. If you need to meet at a time that's not listed, just send me an email. We will set up an appointment and meet. Um, yeah, and final exam available May 12th and 13th. You just need to choose your own 6 hour block of time to work on it. So, yesterday, what we saw was this thing. So this is a repeat from yesterday that you have this thing called the area between curves. So if you start with f of x is greater than or equal to g of x, and if that's true for all x values um, between a and b, then the area between the graphs of f and g, starting at x equals a and ending at x equals b, is given as this integral starting at x equals a and ending at x equals b of, and then the function we're integrating is actually found. It's the function that's being integrated is take the two functions and subtract them, but in the correct order, right? So the upper function minus the lower function. I'm using this language, upper and lower, because if f of x really truly is greater than or equal to g of x, then in terms of the picture, when you draw geometrically, f will be above g, right? F will be the upper, and then g will be the lower. And just as a side comment, if this is true, so if you're applying this formula in an appropriate setting where f is above g, or that is algebraically f of x is greater than or equal to g of x, then f minus g is always greater than or equal to 0. And it goes into a property that we didn't really discuss this semester, so you're hopefully you can just take this one and go, yeah, okay, I'll just believe this to be true. But if the thing that you're integrating, if you have a definite integral and the thing you're integrating here is always greater than or equal to 0, then it turns out that the result of the integral is always greater than or equal to 0. So we'll just kind of go with it. The point here being, when you use this formula, as long as you truly ensure that f of x is greater than g of x, and you integrate f minus g, you always end up with area in the usual original sense of area, always positive. And this is different from when you integrate a single function, you get signed area. I know it seems strange, and if you want to ask about the details, maybe in class isn't the moment, but I could probably say more kind of in an office hour kind of setting for this. But for the most part, I think people will be just fine with when you integrate a single function, you're talking signed area. When you integrate the difference between two functions, as long as the function before the minus sign is always geometrically above the function that is after the minus sign, you always end up with a positive area. It's a little all strange, but it just mathematically works out. So let's just kind of go with that. Um, and here's the thing. Yesterday's idea was, well, this is what you do when one function's always above the other. But today, what do you do if one curve isn't always above and one isn't always below? And we sort of previewed that yesterday, at least the big idea, but you just split up the problem into two smaller problems. I will go so far as to say this. Today, at least the calculus conceptual aspect of what we do isn't all that bad. It's really not that bad. If at all anything, the challenge is in the algebra. It's in remembering how to graph this and that and sort of the particulars of graphing. Okay, so today I think you'll find it's okay overall. The devil's in some of the details, and we'll go through those things. So before doing that, let's just do a one problem review of the type of thing we saw yesterday. So I want to set up an integral to represent the area between y equals x squared minus 2x plus 4 and y equals 2x plus 9. So right away, before doing anything else, I want to do some kind of a graph of this. And by graph, I don't even want to draw axes. Like if I can avoid drawing axes, I'm going to cross that out. If I can avoid drawing any axes and still address what needs to be addressed, then why not, right? So sometimes we don't need as much accuracy as like, okay, there's the origin, and then, where is the parabola located, from the origin? Like, is the parabola kind of more to the northeast or sometimes we don't need that detail. Right now is one of those situations where we just don't need that detail. I see here, for instance, a parabola with a positive coefficient in front of x squared, right? Coefficient of 1. So I see a concave up parabola. If you took the second derivative of this, you'd get positive 2. And then over here, I see a line, y equals 2x plus 9. That's a line of slope 2. Now, my picture here doesn't show slope 2. I mean, this line's a little too shallow for that, but close enough, right? The point is, there's no x values provided in the problem. It just says area between these two. So that's got to be this region here. And in this region, look, there's these two x values right where the intersections are. We'll need to find those. But before even doing that, I want to just point out this one key idea that I think the key thing that tends to get people on this is like, what the hell does he mean by upper and lower? So I'm just going to erase part of this shaded region in here. I mean to shade the whole thing, okay? But normally in class I'd point. I don't have quite that. Right? I can't point at the projector screen. So like, how do you determine what's upper and what's lower? Tends to be the thing that gets people. Let me fix this here. Oh, sorry about this. Okay, so what I imagine you do is, so there's this entire region in the middle that's all shaded, but you start somewhere in the middle of it, and then from here travel up, like travel north, right? And then in this case, you end up hitting the line. So the line is upper for this shaded region. If you start anywhere in the shaded region and you travel downward, travel south, you end up hitting the parabola, right? So start here, travel down, you end up hitting the parabola. So the parabola is the lower curve. It would be different if, like, just to change it up. Okay, this is the region we need to talk about for this question, but just thinking of a different question, let's say we need to talk about this region over here. Okay, if the region I just shaded over here is the one we need to talk about, then you start somewhere in the shaded region, and if you move up, you'd hit the parabola. So then the parabola would be upper, and then the line would be the lower, right? But that's not the region we're talking about. In the region we're talking about here, the one that's enclosed by, oh my goodness, this erasing. I wish the eraser width were a little smaller. In the region that's shaded here that we're talking about, the upper curve is the line, and the lower curve is the parabola. And that's, the point is, the drawings were not very accurate. Like the only idea that was taken in mind here was concave up parabola and a line of slope 2. And just based on that alone, just based on this very rough sketch here, the line is upper and the parabola is lower. And so that already, to me, sets up most of the answer. That the final thing, the integral that we need to set up should be integral from some x value to another, and the upper curve was the line, minus the lower curve was the parabola. Right? This is almost all the work at this point. We just need to find the x values. That's it. Yeah. And to find those x, first, I'll just show the picture this time around. I'm going to change up the order each time today. But this is what a Desmos picture of this looks like, right? So I've got the line in red. So no, that's the parabola. The parabola, x squared. The parabola in red, the line in blue, and the shaded region that we're talking about here in purple. And in this purple region, yeah, I'll highlight the blue line. The upper, so start anywhere inside this purple region here, and as you move up, you end up hitting the line, the blue line. So you maybe start over here, you move upwards, you hit the blue line. Now I'll highlight the red parabola. If you start anywhere in this purple region, like where the mouse cursor currently is, and then you move down, you end up hitting the parabola. Okay. But what we need to find is where these intersections occur. And of course, we could use a computer to cheat it. But like the point is, we don't need this graphing tool to find where those intersections are. What we can do is to find the x values where the red curve and the blue curves intersect, we could set the y's equal, right? Set this here equal to that. We'll have x squared minus 2x plus 4 equals 2x plus 9. Let's get all the terms on the left side. So there's a 0 on the right side. Subtract 2x on both sides, subtract 9 on both sides. You have x squared minus 4x minus 5 equals 0. Factor the left side. You have x plus 1 times x minus 5 equals 0. So you end up with x plus 1 equals 0 or x minus 5 equals 0. Solve those two little equations. You have x equals negative 1, x equals 5. Now, you might have your two x values presented in a different order. That's if you factored where you had the two factors swapped. That's. But like, just keep in mind that the smaller x value is negative 1. So really, the integral should be set up from the lower x value of negative 1 to this bigger x value of 5. Right? And for us, I'm going to say, like, for these kinds of questions, just set up an integral. I try to make this super clear in a final exam kind of instructions right inside the question as well for these find the area between curves. It's enough work to set up the integral. I don't want you to also compute this integral. Like for the computing of integrals, I tend to just say, why not I pick a smaller problem than this? Not that this is bad, not that this is hard to do. It's just tedious. So I try to separate out and have some questions where you just set up the integral and then done, and then other questions where you have to do the integral. But I hope we're okay with this. And, hopefully nice as a review of yesterday's ideas. Let's look at this one. So I've got find the area between y equals x over 3 plus 6 and y equals 10 minus x over 3 and x equals 1 and x equals 9. This first one here, you could write this a little differently just by sticking the x off to the side, right? So this could be like a y equals a third x plus 6. Still the 3 is in the denominator. It was in the denominator before, it remains in the denominator. This one as well, this could be y equals 10 minus a third x. And in fact, this first one here, it's already a y equals mx plus b, right? Slope 1/3, y-intercept 6. This one over here, if you prefer, you can rewrite this as switch the order of the terms, but be sure that the minus is still in front of the 1/3 x. So negative 1/3 x plus 10. We have a slope negative 1/3 and a y-intercept of 10. So what I'm saying is, if we just take a quick inventory of what we have, there's a line of slope 1/3, here's a line of slope negative 1/3, and then two vertical lines. Yeah, x equals a number is a vertical line. So we can look at a picture of it, and I will click the link, and you can see in just a moment. But what I want to do first is let's just draw a rough sketch without the use of the technology, and just say, here, look, these are just lines, and with these provided, you'll have to start trying these to see, should I draw the x and y axes first, or should I not? It takes a little getting used to, but I think here, because we've identified the 6 and 10 as y-intercepts, it'll probably actually help us out to do this. So I've got like y-intercept 6, slope is 1/3. That's a positive slope, but very shallow. So it's like a line that looks like maybe like this, right? And then the other line had a y-intercept of 10, but the slope was negative 1/3. So still very shallow, but negative slope, something like that. X equals 1, probably right over here. X equals 9. We've got to be careful because there's this. When does this happen? And then where's 9? It turns out we'll see in the picture that 9 is to the right of where this intersection occurs. How would we know? So sorry to do this to you, but because this is the first one of these that we're doing, I'm switching the order a little bit because I think the explanation works better this way. So I want you to just kind of trust for a moment that the 9 is to the right of this intersection. We'll see that typically when you attack a question, you might switch the order in which you do some of the things from this explanation. But it's the first one, so it is a little exploratory. Sometimes the order in which things are explained for an exploration are a little different than the order you would actually practically complete a problem, right? So we'll see the more typical order of things in just a moment. But let's click that link and see a picture that looks like this. So I hope you're seeing at least all the features that that have been mentioned. There's this red line, slope 1/3, y-intercept 6. Here's the blue line, y-intercept 10. Slope -1/3, and then x equals 1 is this vertical line on the left, and x equals 9 is this vertical line on the right. So if you look at the shaded region, well, it's not one shaded region, is it? It's two shaded regions. Let me turn off the shading for a moment and just point out that in this, it's the region's it's two triangles, isn't it? I mean, it looks like a bow tie, right? I should have thought about, like, I'm already wearing a collared shirt. I could have fixed my outfit for today. Anyway, whatever. Anyway, yeah. So let's look at one of these purple triangles at a time. So like this purple triangle on the left here, right? So right here, notice that as you travel upward, the upper curve is the blue line. That's the line with slope 10. Sorry, with y-intercept 10, and then the lower curve is the red line, the one with y-intercept 6. So that makes sense because look, the y-intercept 10, like, why is that the one that's upper? Because 10 is a bigger y-intercept than 6. Like, this line, among the y-coordinates, this blue line had a head start, right? Like, even if the slope is negative, it starts up higher. So it kind of makes sense which one should be the upper. And then in this other region over here, so there was the two purple rectangles, but this rectangle over here, let me zoom in just a little bit. In this region, if you start here and you move up, you'll see that the upper curve is red. It's the line with the positive slope, or the line with the y-intercept of 6. And then the lower curve is this blue here. But see, what's going to matter is we need this intersection. And yeah, we could use the system to see what it is. It looks like it should be a 6. But what I'm going to do, just for the sake of discovery here, like, let's just say we don't know what it is. And, in a moment, I called this C. So I don't know. Let's just say we don't know what it is. Again, it's a little bit simulating of things. But the point is, we see this idea that there should be an integral from 1 going up to whatever number C is of the upper line. So that this one here, the one with the y-intercept 10, so this 10 minus x over 3 first, minus, and then the lower one, right? This quantity x over 3 plus 6 dx next, plus, and then the second integral from C to 9 should switch which function, what order you subtract the two functions in. So, I mean, it's a lot of, yeah, the point is, this is the same content just kind of written out, like from x equals 1 to x equals c. The line with the y-intercept 10 is above the line with y-intercept 6. And starting at where the intersection occurs, starting from c going up to x equals 9, the two lines have swapped, which one's above and which one's below. So now the line with y-intercept 6 is the one that's above. So where do these intersect, right? Where do these lines intersect? Again, we saw it using the graphing tool, but really what we do is we're doing the same algebra process we just did for the last question, just for a different purpose. We want to see where these things cross because that's going to be the split where we have to set up two versions of the problem. We use the formula from yesterday twice, so we'll set y equal to y. Yeah, x over 3 plus 6 equals 10 minus x over 3. A couple ways to solve this. I went ahead and added x over 3 to both sides and subtracted 6 on both sides. So you have 2x over 3 equals 4, multiplied by 3 on both sides. You have 2x equals 12, divide both sides by 2. X equals 6. So that's the c, right? So we've got this integral from 1 to 6. The above curve, the upper curve, is the 10 minus x over 3, then minus the lower curve, x over 3 plus 6. The other integral, starting at where this intersection of 6 this x-coordinate intersection of 6 all the way up to 9. The upper curve is the x over 3 plus 6, and the lower curve is 10 minus x over 3. So I hope this works as like applying the formula, yesterday's formula twice, is really the big conceptual idea. It's not too bad, right? Like it's just, if one function isn't always above the other, all you got to do is just make more than one integral, right? Split up the x interval. We instead of doing one integral all the way from 1 through 9, that wouldn't have worked because one function wasn't always the one above. We split it up, noticing that 6 was the right place to split things, right at x is equal to 6. Make sure we're okay before we just look at another example. This one was a little out of order, let's just say, right? Like, I put it in a certain order just so that we could see a picture kind of early-ish on, and then it's not probably the order I would have done things if it's time to get to work and do a problem, but it was probably a decent order to explore what's happening. The next question, I would like to actually do this in an order that, I mean, there's lots of like people have different ways to think about these. Don't get me wrong. Like you can think about the concepts in a different order than I do, but at least I would like to present this next question in an order that certainly works, right? Like now that we saw some of the wacky features in the previous question, we've got, let's say in this one, find the area between y equals x minus 8 and y equals 4 minus x squared and x equals negative 8 and x equals 6. So first of all, we've got this, that's a y equals mx plus b, right? We've got a line of slope 1. Over here, there's a parabola because we got this x squared. You could say because of the minus in front that this is an upside down parabola. I'm going to say if you took the second derivative, you get negative 2. If the second derivative is negative, you're concave down. So I'm going to call that a concave down parabola. We have a line of slope 1, positive slope line, and then we have a concave down parabola. So here's my line of slope 1. Here's concave down parabola. But this picture's very rough, right? Like I didn't draw axes, and there's this shaded region, but see, unlike the first question we had today for review, it's not just we had a line and a parabola and that's it. We also have these two vertical lines. X equals a fixed number. X equals the number 6 vertical lines that are given. And so we have to be a little more careful for this question. So let me actually say this, like before we do anything else, I want to figure out there's these two intersections. Where do these occur, right? Like, I mean, if this x value is, so based on whatever this x value is, we don't know right now. We're going to find out in just a moment. But like this x equals 6, is it over here, right? Question. Or is it to the left of this crossing, right? So where is this crossing? And then where's this line x equals 6 in relation to this? Is this to the right or to the left? Those are some of the things that I don't want to just guess at. I want to know, right? So let's first, before drawing in the vertical lines, I think it makes more sense to, because we don't know which of these, maybe even x equals 6 is all the way over here. Who knows, right? Like unknown. So let's just figure out where the intersections are first, right? So as a first step, I want to take the tilted line, but like these are the vertical lines. So I mean, a line of slope 1. Take the parabola, see where they intersect. So set these equal. I don't like having the negative in front of the x squared, so I'm going to add x squared to both sides. X squared plus x, subtract 4 on both sides, equals 0. Right? So you've got a 0 on one side. We can factor this. X plus 4 times x minus 3 equals 0. So x equals negative 4 or x equals 3. So what I can already then, let's go back and draw that much of the picture. So it was a line of slope 1, positive slope anyway, right? And then a concave down parabola. And the point is that these two intersections, well, okay, there's two intersections. Well, this intersection over here on the left, that's the one with the negative x coordinate, right? That's the smaller x value. So this point is negative 4 for the x value. The y coordinate, I don't know. I could find out if I want to. Just plug in negative 4 into either of these to find the y value. It turns out we don't need the y value, so let's not even bother. This other point here, right? This other intersection is the intersection that's more to the right, and so that this point has x coordinate 3. What's the y coordinate? We could find it, but we're not going to need it. But now knowing that this point right here has the intersection occurs with an x coordinate of 3, then this x equals 6 we can see is to the right of that. Yeah. So the vertical line x equals 6 is going to be over here somewhere. That's x equals 6. Now here's the thing. In the picture, sometimes what happens is people draw their parabolas a little too steep, and their line never touches this. The curve, the parabola that some people draw, never touches the vertical line. If you think about it, the parabola eventually needs to cross the vertical line. I mean, this may not look all that accurate to have the parabola look so straight, because the parabola never looks that straight. It's always curved. But it's hard enough to draw some of these pictures, and let me say it this way: it's more accurate to have them intersect than it is sometimes what people are sometimes in the habit of is drawing their parabola so steep that these never intersect at all. That's less accurate because these do intersect. And let me argue why these intersect. Well, think about if all you do is you're like, if you were unsure how to draw this parabola, what you could have done is made a t-chart, right? And every time you pick an x value and you plug in to 4 minus x squared, you get a y value. So no matter what x value you pick, you're going to get a point. That's why, that's, if you think about what that means, you get a point where the x coordinate is 6, you can get a point where the x coordinate is 6.1. So you should get a point on the parabola even with x coordinate 6.1. So the parabola eventually has to go past the line x equals 6. And so we should draw that feature. Same deal, x equals -8. Well, that should be to the left of this intersection, right? So -8 minus x equals -8 may be somewhere over here. And again, sometimes people make the error of not letting the parabola cross the line, but this parabola does cross the line. So it would be a little more accurate and helpful for us to draw like this. So there's this region, and there's that region. 3 regions. Notice in the first region, so we're going to set up an integral from -8 to -4. And in the first region, the line is above, and the parabola, it looks so straight here, but it's really a parabola, right? The parabola is below. In the middle region, you move upward, and you'll see that the parabola is above and the line is below. And then in this third region over here, you'll see that the line is above, yeah, and then it's starting the shaded region, you move down, the parabola is the thing that's below. Yeah, so actually because of the 3 separate shaded regions, we're going to set up 3 integrals. So based on these, I'm going to say it and then I have to reveal it on the slide. This will start an integral from -8, end it at -4. The second integral is from -4 to x equals 3. The final integral is x equals 3 to x equals 6. Right? Integral from -8 to -4, an integral from -4 to 3, and an integral from 3 to 6. Let's just make sure and confirm with a picture what's happening is. So I've asked the computer to give the line y equals x minus 8, the parabola y equals 4 minus x squared, the 2 vertical lines, x equals -8, x equals 6. So I hope you see all these features, and the shaded region, you see these 3 parts. You're going to see we're going to need to set up 3 integrals. And in this first region over here, so start somewhere in the middle of this region, and you move upwards, and as you move upwards, you end up hitting the red line. If you move down, from the purple region, you end up hitting the blue parabola. For the middle shaded region, as you move up, how do I do this? As you move, there we go. As you start in the purple region, the second purple region, you move up, you hit the parabola. That's the upper. And then the line is lower. In the third region, the upper curve is now the line. Right? So it's because there's the swapping of which one's above and which one's below that we actually need to set up 3 separate integrals here. Right? So we're going to have, as final work, something that looks like this. So I use a smaller font so it all fit. But let me put this up so that we can kind of compare, right? So let's take this middle integral from -4 to +3. Okay, so we got those by algebra. The x coordinate of the intersection -4, x coordinate of this intersection was 3, and here the parabola is the thing that's upper and the line is lower, and that's why it's over here 4 minus x squared, the upper minus the lower was the line. You'll see not so for this third integral, the final integral, for this purple region off to the right. Um, it starts at x equals 3 and ends at x equals the provided x equals 6 was provided in the problem. So 3 to 6. Now the upper curve, though, is the red line, right? So you got the upper is x minus 8. The lower curve is the parabola, y minus x squared. So I hope that kind of overall works for folks. Some of these, there's danger of like over explaining. So I wanna again, like, I know the question says find the area, but like the point I think here is like, could this integral be done? I mean, well, it's three integrals. Could it be done? Yeah, there's nothing so bad about looking at the indefinite integral here, looking at an indefinite integral. There's no substitution, just power rule like business. It's not bad. It's just tedious. There's three integrals, and all three integrals have four terms in them. So I think this is a good place to stop this problem, is what I'm saying. Could we complete this? Yeah, in principle, of course, but it's just a lot of writing. So I'd like to ask, well, if you have questions, you let me know, but I'll post this and ask you to try this, right? So find the area between y equals x plus 6, y equals 18 minus 2x, x equals 2, x equals 7. Draw a picture. You decide, how accurate you want the picture to be. So, do you want to draw axes in? Do you not want to? I mean, think about what kind of curves you have. Do you have parabolas? Do you have lines? Use that to help determine what you want to do. All right. I'm going to share some thoughts on this question. There are four lines here, right? There's no parabolas. Because it's all lines, I went ahead with my thought was to draw a sketch of this, including the x and y axes. Again, there's lots of different approaches, so I'll just say like if the steps that you have don't follow what I have in the same order, I think there's a lot of ways to explore what the graph looks like. And so you got to do what works for you. Sometimes you start drawing a picture and then you decide, I need to make it more accurate. So then you include axes or you redraw, noticing a feature. Things like this happen a lot in these sorts of questions. But I will say we've got a line whose slope is 1. We have a line whose slope is -2. This first line, slope 1, y-intercept 6. Second line here, slope -2, y-intercept 18. So already, like, let's see, y-intercept 6, slope 1, something like that. Y-intercept 18, however, slope is -2, so that should be, it's negative but steeper. The picture barely shows that that's steeper. It's not going to matter a whole lot. Then x equals 2, x equals 7. Wait, but where's this intersection? So I kind of want to find that first. You know, like if we could just figure out what's the x coordinate where these two lines cross each other, then we could figure out what to do with x equals 2 and x equals 7. Right? So my thought is like, now, where do these lines cross? So set the y's equal. X plus 6 equals 18 minus 2x. Just to have positive signs, I'll add 2x to both sides. So 3x equals 12. X is equal to 4. Right? So already then in the picture, let's just start to redraw here. But 6, 18, those are the y-intercepts. We had a slope of 1. We had a slope of -2. Again, you know, accuracy, it's accurate enough for what we need to do. We just need the picture accurate enough so that it's not lying to us so that we can set up the integrals properly. So this intersection here occurred at an x coordinate of 4. That means the provided line x equals 2 and provided line x equals 7. So 2 should be to the left. There's the 2. Somewhere over here is a 7. And even this line with x equals 7, does it happen before or after the x-intercept? We could find out if we really wanted to, but it's not going to matter. We just have a shaded region there and a shaded region there. The key thing being that in the first shaded region, it's the line, there's a switch of which line is above and which line is below, but the line that's above first for the integral from 2 to 4, it's the line that had the bigger y-intercept, right? The y-intercept of 18, right? In fact, that's the way I wanted to argue this. So you see this in, I forgot that's how I was going to argue it, that the line 18 minus 2x rewritten as y is equal to -2x plus 18, that is a y-intercept 18. I'm speaking this language of it has a head start because of the bigger y-intercept. So that's the line that should start above. At x equals 4, they switch, right? So we saw that's where the two lines intersected, and so then all of a sudden the line that was above is going to be the line that's below. So I'd say already, with just that much of a sketch, like this should be a final answer to this. Right? We could compute the number, but like this is the integral setup, the two integrals. So integral 2 to 4 of the line that's above, the one with the head start, y-intercept 18 first. That same line is the line that's below for the second integral, right? So for the integral from where the intersection occurred at 4, ending at the provided 7 in the question. I hope that works kind of for folks. That like, if we looked at what that looks like, right? So there's the line of slope 1 with y-intercept 6. There's in blue is the line of slope -2 with y-intercept 18. The shaded, x equals 2 vertical line, x equals 7 vertical line are shown here. We see that intersection happening with an x coordinate of 4. And there's these two triangles, and in one triangle versus the other, right? For the triangle on the left has the blue curve above and the red curve below, whereas the triangle over here like has the red curve above and the blue curve below. Right? This looks like this bow tie's had a long day. That's what this one looks like. Yeah, hope we're doing all right with that. I'll I'll look to see if anyone's asking questions. I'm not seeing anything so far. All right. Um, I have some more challenging questions in how timing is working. Normally you'd have the rest of class to do all of these, right? Like, and you get through one or two, but like I, with how the semester is going, I'm gonna change things up a little bit and say, okay. Oh, sorry, I should say this. Just generally the story here is you should take the question you're asked, sketch a picture first, draw enough of an accurate picture to determine is one function always above or not. Because sometimes people then work too hard using today's method and forget about yesterday's thing. If one function is just always above the other, you only have to set up one integral, right? So you got to answer first by drawing a picture: is one function above the other always? If so, one integral. If not, split into several integrals. So here's some practice problems that I would encourage. There are some challenging ones. I would encourage you to try them later. There's a link provided. It does not work yet. If you click on it, you'll just get to a file not found kind of error. But I will post a PDF there, and I will do what I can to, as thoroughly as possible, explain the reasoning behind and like how I discovered. Like I'm gonna provide part of a graph and then like talk more and write out some words and then show you an updated graph and so on, right? So I'll do what I can for these. Normally you'd have some time to practice and I'll walk around, and there are some challenging ones I just know because people usually ask about these. But what I wanted to do, because, well, timing is what it is talk about an application. All right, so we lose a week of the semester, right, from how things were going. And I had to make some decisions during spring break about what to cut. And it pains me to cut what I had to cut. And I'll say this: it was either what we covered today and yesterday was the area between curves. It was either cover that or cover an application of an area between curves. And the real problem is you can't really just do the application of the area between curves without talking about the area between curves. So it's called applied calculus. Yes, I want to do more applications. Don't get me wrong, but it wasn't going to be possible to do all the things. So I decided, how about this? I want to take the next 4 minutes to talk about the application. You are not going to be responsible for the application, right? Like, I want to talk about it. It's interesting to me. I think it's interesting from just a general citizen of the world perspective. It's an application that the professors in College of Business Administration really want us to cover. And I think I can say enough about this so that when you see this in a future econ class, you're good to go. That's what, yeah. So again, the next several minutes of what you hear, you're not responsible for it on a quiz or a homework or a final or anything like that. Okay, I want to talk through it, and I think even this short explanation would not have made sense if we didn't practice the skill of area between curves. So what happens in econ is you draw these graphs where the y coordinate is price and the x coordinate is quantity. This seems swapped for most people's minds, but the econ people say this is the way to do it. I won't go into the reasoning why, but when you do that and you have price of an item, price per item on the y-axis and quantity on the x-axis, you have this thing called the demand curve. It's shown here in red, and the demand curve always ends up being a decreasing function. I don't want to get into the details of why, but this demand curve basically explains you've got these consumers, the people who are willing to buy something. And it tells you, like, at a certain price, this many people would buy. At a different price, this many people would buy. Like, once something gets prohibitively expensive, fewer people want to buy it, right? Like, that's what this demand curve is, and it's always a decreasing function. There's also a supply curve. It always happens to be an increasing function, and it tells you about how price per item relates to the quantity again, but not of like people who want to buy, but rather people who want to sell. And because you've got this decreasing function in red, you have this increasing function in blue, it always turns out that the two curves are going to cross. They're going to intersect at one place, which is called the equilibrium. Right? So that intersection shown here is the equilibrium. And you can as people, not just in econ, but people in business actually really want to know. Like if you go into business and you're going to sell anything at all, right? Like even a conferencing app or whatever, right? You need to find out this because you want to find out how much you got to charge for the product that you make. And so you would find this intersection. It's an algebra problem. It's the same algebra problem we've been doing. You set the y's equal, you solve for x. And if you solve for x, you find out how many things you should make so that you don't make too many or too few. And you also find out what you should set the price to be. You find the y coordinate by plugging in your x value. Anyway, you can find both the x and y coordinate of this equilibrium. But then the thing to really talk about here is there's this region over here, consumer surplus. Let me talk about this real brief and just say, what is this? Consumer surplus. It's an area, right? The area between curves. The units on this is actually in dollars. I don't want to dig into that either. I just want to say what this is on this demand curve, there were these people over here, like these points on the red curve, represent people who were willing to pay more money for a certain item, but they only had to pay market price. So these people were like, oh, I was going to pay this, but I only have to pay that. And so they feel like they'll buy the thing for sure, and they'll feel like I won. They're like, I beat the system. I didn't have to pay as much as I needed. I was willing to pay. I only paid this amount instead. So if you take all the consumers, all the people who are going to buy the product all together, and total up, tally up how much in terms of dollars they felt like they won collectively, you get this area right here. To compute this area, again, you're not responsible for it, not in this class, but I just want to talk through it in cartoon version. It's like it's an area between curves. What you do is you set up an integral from x equals 0, because that's the start, to x equals, well, whatever the x coordinate is here, again, found by algebra, just like we've been doing. And then the integral, so that's the x values for the endpoints of the integral. And then the upper curve is the demand curve, which is provided in the problem. And then the lower curve, it's actually the horizontal line. It's this y coordinate of what the market price was at equilibrium. That's an area between curves. In the same fashion, there's this blue shaded region called producer surplus. It's the same deal of like down here, these points on the supply curve represented producers, people who made a certain product. They're like, oh, I would have sold this for this cheap, but the market says, equilibrium says, I should set the price higher. Sweet. I was going to sell this for only $10, but I can sell this for $80. And they're not cheating the system. It's just that's the fair price. It's what people are willing to pay. It's actually fair. But because these people were willing to sell this for way cheaper, but they got to sell it for more, this region shaded in here, it's in dollars, represents the amount that the producers feel like they won over the consumers. And that is again, it's an area between curves. It's set up as an integral, right? Integral from 0 all the way up to this x value here. And then the upper curve now is the horizontal line, and the lower curve is the supply curve, which would be provided in the problem. So, I mean, again, this is all a little bit cartoony. Sorry, like we're not going to cover it beyond this, and you're not going to be responsible for it at all in this class. But I think the point is there's enough here so that if you did have to do this in a future econ class, then you can take the skills-based thing of area between curves, and even this, I think, in a nutshell explanation, and deal with it then, right? So. Yeah, again, sorry, that's kind of some of the decisions that had to be made. You'll hear a little bit tomorrow about some other decisions of what had to be cut. I'll just say, yeah, today's Wednesday, so there is an online quiz tomorrow. I'm just reminding you of that. And I would strongly suggest starting WebWork 44 today. It's the last one. It is an extra credit one, but start it today so you don't have to deal with it on Monday. Right? And then office hours are here. Or if the times don't work, send me an email. We'll set up an appointment and meet. And then I will, I haven't gotten around to, oh my goodness, I need to post some practice stuff for the final. I haven't done that. I'll do that by the end of the day today. Sorry about that. But yeah, final exam, you choose your own 6-hour block of time sometime next Tuesday or Wednesday. All right, we'll end a little early.